Hello and welcome to video number 12 for the Foucault's Pendulum for Advanced Experimers. Today's video will be looking at an introduction to node bias. Node bias is without question the most important parameter of the Foucault's Pendulum, but today I'll just be introducing it to you and not going too much into it, just an introduction. We'll also be looking at results from experiment number 11 to explain what happened there. If you remember in number 11, we had the pendulum was swinging with the launch index indicator swinging in this direction from the string, or the relaunch from we burnt that cotton string, but the pendulum actually turned. And during that swing it spun like that. However, it maintained this direction the rest of the swing, right? Now I was a bit apprehensive because I detected this movement in the pendulum from swinging from the index launch indicator had moved. Now we're allowed a little bit of play with the launch indicator, but to do that 90-degree swing was alarming, so I considered that I may have had a launch bias, or a node bias in the system. So I didn't call the experiment a success, and I did not claim the anti-clockwise direction, which would indicate the Earth is spinning. So I think that's important, but I think now a very important factor is for anyone who may be into physics, could maybe explain this. What we know from Foucault's pendulum is that, and the whole concept of Foucault's pendulum is that the pendulum, when it's swung, it has mass and momentum, and that is the whole concept of the Foucault's pendulum, that this mass will just keep moving independent of the Earth. It will, as long as we can provide motion, it will just keep going in that same vector that it was launched at, and if we can artificially pump it and keep that vector in that same direction, the Earth in theory should move under it, independent of the launch indicator moving, provided it's not spinning around going crazy. So for those people into physics are a bit more advanced than I am, if you'd like to comment on that. Also, we'll be looking at a precision run. This will be the first time I'm setting up the laser that you've seen this precision with the more metrics, and I think it will be more helpful if anyone's sort of into a university or schools. They may have not seen this done with the lasers. We'll also be doing a complete run, start to stop, so you'll see the whole pendulum swing through its full cycle, and there's a lot of many metrics to be gained from that, I can tell you. Also more, as I said, more metrics. Now, where we are now, we are into a very advanced knowledge of the Foucault's pendulum. I think we've left YouTube behind. We've certainly left all the educational institutes behind, and you won't find this information in any books. So we're now on a new direction, and I know for a fact from my research I am definitely on my own. Okay, so let's move straight on to, and I'll just give you a quick introduction into that bias node concept. So here we go. So here we are trying to demonstrate this node bias system, basically a jam tin with a line through the centre. It's clearly biased because it's lifted on one edge through this pad. Now let's imagine I didn't know the pad was there, and I purchased a ball bearing to see if this thing was level, and I launched the ball bearing here. The ball bearing ran anti-clockwise. I thought, okay, maybe the ball bearing is faulty. I'll choose another type of ball bearing. Here we go, I've purchased a very precision zirconium ball bearing. Okay, it goes anti-clockwise. Oh, okay, so all pendulums in the southern hemisphere or all ball bearings in the southern hemisphere must swing with the Earth anti-clockwise. Maybe I try the other side. of the line, or on the line. You know, if I was actually fluked the line, it would roll straight down. But that's very hard to do. You've got 360 degrees, and fluking that point is very hard. So I tried my ball bearing on the other side, and oh dear, look at that. The ball bearings in the southern hemisphere swing clockwise. I'll go and buy a better ball bearing. Yes, look at that. Ball bearings in the southern hemisphere swing anti-clockwise. So here we have a clear node bias, which is this foam offset. We can get precise now with many factors in the pendulum that can add minute degrees of bias. Now that's what we have to eliminate. The pendulum that I have made is very, very precise, and it's been designed to remove as much node bias as possible. Now, any residual node bias, in theory, should be overcome by the Earth's rotation and the principle of Foucault's pendulum. So that's what we're up to now. We're investigating that. Can the concept of Foucault's pendulum and the mass of a vector travelling through space with minimum friction overcome any bias? Before we start the experiment, I'll just quickly go over the setup for those who may not be familiar with it. We have our pendulum. To the right we have camera recording the deviation, left to right, clockwise, counterclockwise. The laser and the launch chair. The fibre optic cable going to the swing chamber, swinging mechanism. Much more detail in other videos if you would like to go to them. Okay, now I'll set up for the launch. So here we are, ready to launch. Distance from the plumb bob to the door is 2300 millimeters. Just checking my illumination on the pendulum. The laser is illuminating the pendulum all the way. Okay. I've included the horizontal line. I just tweaked that by the launch by a fraction. Just check that. We're hovering halfway, it's pretty good. And we're actually 65 millimeters from the launch knot to the launch barrier. So ready for a burn. Pendulum has steadied. And the pendulum is away, swinging. And the launch index on the pendulum has not moved, it's still in line, as you can see by that cotton on the pendulum. Okay, we'll now switch over to the camera on the wall, because I think that's what's showing everything. The true metric now is the one on the wall, so we'll switch to that camera. So here we are, ready to launch. Distance from the plumb bob to the door is 2300 millimeters. Just checking my illumination on the pendulum. The laser is illuminating the pendulum all the way. Okay. I've included the horizontal line. I just tweaked that by the launch by a fraction. Just check that. We're hovering halfway, it's pretty good. And we're actually 65 millimeters from the launch knot to the launch barrier. So ready for a burn. Pendulum has steadied. The pendulum is away. Swing. And launch index on the pendulum has not moved, it's still in line, as you can see by that cotton on the pendulum. Okay, we'll now switch over to the camera on the wall, because I think that's what's showing everything. The true metric now is the one on the wall, so we'll switch to that camera. So we're dancing between one centimetre on the left, which is a green, to 2.5 on the right. Everything is looking good, like a anti-clockwise direction. We have our shadow on the excuse me, the shadow on the red side is wider than the green side, which is looking good for anti-clockwise. And the swing is clearly now going anti-clockwise. We're up to 5 units on the right and 2 on the left. The wider line on the right hand side is because the optical fibre holding the pendulum is closer to the laser on the right than it is on the left, so it's a narrow beam on the left and wider on the right. This is what we should see for anti-clockwise direction, along with the fact that it's obviously moving more units to the right than it is to the left. So that would clearly indicate to me a anti-clockwise direction, which is what we expect for the southern hemisphere. I wasn't around to catch the plumb bob move up the vertical line, how far it got, but it appears to be shadow down the bottom there around about, I don't know, can't see from here, but I can be able to look on the camera, but you can see the down the bottom, the bob is actually shadowing more to, as it decreases in amplitude, it's actually moving to the left, again showing anti-clockwise. Because the pendulum is decreasing amplitude, we cannot do that Foucault's calculation for our latitude, because the pendulum is decreasing in amplitude all the time. However, it's very obvious that the pendulum is moving anti-clockwise, and if I was to repeat this 100 times, I get the same results. That's how precise the pendulum is at this stage. So for everyone who wants to keep watching, I'll just let the camera run until the battery runs out, or whatever happens. I might just kill the lights to see if that makes a difference to that shadow. I think it has. I think it's made a difference. I might just use my phone camera now just to give you a shot of the pendulum crossing the laser line. Very clear now, the pendulum is crossing the laser from right to left. Very clear now, the pendulum is crossing the laser from right to left. Right to left. Again indicating anti-clockwise motion. Alright, we'll go back to the other camera now. Right to left. Again indicating anti-clockwise motion. Alright, we'll go back to the other camera now. Okay, I'm back to the other camera. We're getting 35mm to the left and 45 to the right. Now the pendulum is now slowing down. However, there should be enough momentum to overcome any are those node biasing issues that we discussed in friction issues, and the mass of that pendulum and the momentum should override any of the minute inconsistencies in bearings that I have not been able to find. I'll just interrupt now and take another shot of the pendulum. Side on to give an indication of the swing amplitude. Okay, so we have our swing amplitude, about half a metre. I haven't been following the time because there's no use timing this at this stage, because the YouTube clock will indicate as there's been no interruptions. Okay, so we have our swing amplitude, about half a metre. I haven't been following the time because there's no use timing this at this stage, because the YouTube clock will indicate as there's been no interruptions. Alright, now we're getting to a strange anomaly. We appear to be having more deviation on the left than the right, which will indicate that the pendulum has gone through some crossover stage. Now, you will never see any of this on YouTube or from universities. They all hide this. This is very controversial. If I was interested in this, in the conspiracy side of this Foucault pendulum, I would record this video and take a copy. Please copy and distribute these to anywhere you want. But now we're seeing as the pendulum is actually slowing right down. It's settling back to a centre point. Or in fact, it's actually starting to progress clockwise. I'll just give you a shot of the momentum. I believe there's still enough momentum in the system. Might be able to focus at it closer. Okay, so it's very clear now that it's moving clockwise. No one lets their pendulum die at this stage. So I'll just give you a side-on shot. The pendulum is swinging possibly 300 mils and more than most, probably equal to most grandfather clocks, for those interested in clocks and pendulums. Still enough momentum, I believe, to overcome any of those minute biasing factors. The pendulum is swinging possibly 300 mils and more than most, probably equal to most grandfather clocks, for those interested in clocks and pendulums. Still enough momentum, I believe, to overcome any of those minute biasing factors. Back to the other camera. Right, now we've seen the pendulum go through its... I missed it because I was doing that other shot, but you would have seen the pendulum go through its centre phase, where the line would have been moving, exactly hovering across the centre point. Now it's clearly moving stronger to the left than it is to the right, which now indicates the pendulum is swinging clockwise. So please record this and distribute to those people who are interested in flat Earth and if the Earth is spinning or not. Quite controversial. You will not see this anywhere else. I am not calling the Earth is flat or spinning or whatever at this stage. As you know, I have an open mind and I will be doing more experiments to eliminate more errors that I have in my system. And before I make a call, myself personally, I will be, I guess, convinced 100%. As you know, it's a very controversial subject. Foucault pendulum is goes very deep into conspiracy. Quite an interesting book was although I haven't read the book. It goes into the Foucault Pendulum book. It goes into conspiracies as well. Okay, so we have clear indication now of clockwise direction. I'll give you a shot with the camera crossing the line clockwise from my phone. Clearly crocking, going left to right, clockwise direction. No flashes when it hits the centre point. Definitely clockwise. Clearly crocking, going left to right, clockwise direction. No flashes when it hits the centre point. Definitely clockwise. That amplitude is almost going back to the same amplitude deviation that the original launch was. The question of whether I have struck a node bias is still in question. What happens with a node bias is the pendulum will swing to that centre point. I managed to resurrect the camera again. We're in the last swing of the pendulum. Two to the left, to the right, to the left, to a bit more, a little bit more to the left. The camera gets overheated, so it's almost becoming 2 to 2 on the left and right, which indicates the pendulum is now almost coming to a standstill, and the centre line will become the dominant shadow. The pendulum is very close now to stopping. I might end the video very soon because it does take a long time to actually stop. Pendulum is very close now to stopping. I might end the video very soon because it does take a long time to actually stop. Okay, I think still going 2.5 on the left, 2 on the right. Strange. What? I guess there's enough momentum in that bob just to maintain that for a long time. The friction is so low. The next video I'll show more on the friction. That'll be video number 13. But that is still maintaining that. I've never seen that. I have probably never noticed that. The attenuation. There's still a lot of energy still in that bulb. Yeah. I guess for those people into physics could actually count their residual energy. You've got the weight of the bob, and it's moving about. I can't really line. I guess 100 millimeters still. Okay. It hasn't settled down to the equidistance left and right, but still maintaining a strong bias on the left. I shouldn't use that word bias. More energy on the left, which indicates clockwise. I guess this video is forcing me to watch this. I usually walk away and do something else. I'm painting at the moment, so it's more interesting, painting, watching the paint dry. Okay, that is definitely strong. Still strong. I might try and get a shot. Look, the next video 13, there'll be videos from the roof, cameras from the roof as well. So this is for those diehards who just want to keep going, who are really interested in the pendulum. The true flat earthers probably would be interested in this. The shills and all that, they're not interested. The ones out there who are you know, I guess the control opposition is what some people call them. Remembering now, we're close into the ratio of what the pendulum in Paris was at. The pendulum, Foucault had a 67 metre long wire holding the pendulum, and from memory I think it does 10 metres. So it's 1:6. Now, is the pendulum working truly as a isosynchronous, whatever, what's that, isochronous, I can't pronounce that word, isochronous? I believe it would be still. It's still, it's acting truly as a pendulum. So it definitely is an isochronous device. I haven't detected any figure 8 in the pendulum. It's very hard at this speed, at this velocity, but I can tell you now there appears no figure 8. Now that's quite a controversial subject. It's been discussed a lot, whether a figure 8 should be in the pendulum or should it not be. I believe the one in Paris doesn't have a figure 8. The pendulum crosses a centre line all the time, and it comes back on itself without doing that figure 8 at the end. Again, a very controversial subject. There's equal counteracting arguments for and against the figure 8. I'll keep going with the pendulum. The camera is still hanging in there. Still strongly indicating a clockwise direction. 2 to 1.5. I would have thought by now, if the Earth was turning, it would have actually started influencing it. We've been running quite a while. No, it's at that. The more I study this pendulum, the more crazy it makes me. We're coming now almost equidistance. I think I'll get ready to switch off. You diehards, good luck hanging there this long. I have some questions for you for number 13. Please comment for number 13. And I'll try and set up some more. You can tell me what I'm doing wrong or what you're not happy with. As we get closer and closer to this becomes more controversial, as you know. We're treading on a lot of people's toes, and no one has gone this far with the pendulum. So all eyes will be on me soon, so at the moment I'm sort of in the shadows. YouTube's already started hitting me because I mentioned pi squared instead of g. They don't like that, so that affected my views. The moment I mentioned pi squared, I knew that would stir them up. They don't like that. Alright, we're getting close to equidistant swing now. Well, we've gone this far and the camera's hanging in, so I think we'll keep going. And all I can do is narrate this, so you must be bored with me. The launch indicator is still exactly where it was. Nothing's moved. I'll just give you another shot of the pendulum since we've got this far. Slight little bit of movement, as you can see. Still that flash is the centre line, and it's definitely, yeah, it's definitely slowing down to equidistance, I can tell. Alright, I'll just run this out and let's see what happens. Alright, I have to go now, so I've got other jobs to do, so I'll just turn this off, but I'll meet you on the whiteboard. Quickly before I close down the camera, I might just show you this friction of this bob. Here's my little tool that I used for the friction indicator, the previous experiments. Now I can move this bob without this bending. There's virtually zero friction on this optical cable. Now Foucault never had the optical cable, but he did have a special cable that was a mono cable, I believe, or a specially wound cable. Unbelievable. There's less friction on this than the other experiments I was doing. They actually bent the piece of wire. Okay, I think it's enough. Oh, okay, yeah. An interesting, I did sort of play around with the Cavendish experiment a little bit, and I was going to use this frictionless optical cable, and I was getting inconsistencies with what Cavendish got. So there's another experiment that needs to be questioned a bit. This cable system is much more efficient than anything I've seen to do the Cavendish experiment. Alright, I think it's enough. We'll meet at the whiteboard now. Okay, so was I experiencing some sort of node bias? Node bias is very hard to do. You really need mechanical assist. You need to run at least 36 hours at least, because what will happen is the pendulum will swing clockwise or anti-clockwise depending on your pendulum, the hemisphere you're in, and it could give you a false reading. It'll swing to that node and then it'll lock there. So by doing a 36-hour test with a mechanical assist, the pendulum will either drop into the node and not come out of it, so okay, that's clearly I've got a node bias, or it'll go past the node and come back around and give you a full circle, which means clearly that you weren't in a node bias. So again, the gold standard for testing a node bias is a full mechanical boost pumping, and but your small checks that you can do, like I did with just the initial mechanically unassisted, I think I've given you enough data there or information how to show you're not in a node bias. A very strong indicator that I wasn't in a node bias was that I had my, if you notice that little friction test I did at the end there with that little wire, the optical fibre attachment to the plumb bob is so low in friction, I believe that the launch indicator should be able to swing independent of the Earth and give you a true indication, even on a short run of 50 minutes or so. Now, we didn't see that on our. We never show our launch indicator stayed stable all the time, didn't it? It was in one position. It didn't move. So theoretically, the Earth should have moved underneath it. Anyway, we're too early to call anything at this stage, so we'll move on. I didn't check whether I was in isochronism. My swing time should have been the same at the start as at the end. I didn't check that. You could do that if you want on the video, but again, that's a very important parameter. You have to get that one right. Also, it's probably so much controversy about this pendulum. Before I go on to 13, I might just do a short video to show you what I've come across. That's the controversy about the pendulum itself, as far as a religious point of view and just the flat Earth and just in general physics. So I might just do that before I move on to 13. Anyway, thanks a lot, and we'll see you in the next video. Thank you.